Welcome everybody. Welcome everybody to the latest instalment in the Exeter Causality seminar series. It's a real pleasure to be able to welcome Rhian Daniel in person to the University of Exeter. Rhian is a reader in medical statistics at Cardiff University Medical School, and she is a world-leading expert in causal inference methods, so trying to use observational data to learn about causality. Yeah, she's a real expert in many different areas, including mediation analysis, thinking about time-varying confounding, machine learning methods, and she is also a former recipient of a Henry Dale Wellcome Fellowship and a Royal Society Fellowship. And you're going to be talking to us today about a new method which you're calling regression-by-composition. So I'm really excited to hear about this latest work of yours. Please take it away, Rhian. Thank you.
Thank you very much, Jack, for the far too kind introduction. It's really, really lovely to be here in person and at a seminar for the first time in I don't know how long. So it's really been very, very nice to make the journey here. And thank you to Mark for organising such a wonderful series, and to be included in it is a real honour. So thank you very much, Mark, for the organisation. So yes, as Jack said, I'm going to talk about regression by composition, and it's very much not my work alone by any stretch of the imagination. I think we always start by thanking co-authors, but this is even more important today than ever for me. So this work really was started by Anders Whitfeldt, who had all of the sort of initial ideas around everything I will talk about today. And then he approached a few of us wanting some more formal statistical input into the developments he was making. And I got involved, could see it was really interesting, but I felt I lacked the sufficient degree of formality that was needed, which was why I suggested that Daniel Farewell, a colleague at Cardiff, should get involved as well. And he did with great gusto. So a lot of what you will see today is the result of Daniel's input to Anders's ideas with and Mats and I have just really enjoyed meeting with them and thinking about this stuff with them as well. But really much of the thanks is down to the other three. Yeah, so it's a new framework. Well, you know, is anything ever new to us? We think it has some novelty to it. I'm sure linking very closely to what other people have done already, but a new framework for thinking about regression models that we think is very general. So it includes pretty much any regression model we can think of, but please let us know of things that you can think of that don't fit into this framework, because that would be very interesting to know about and think about too. But we think also has some new regression models within it that might be of interest in particular situations. So I guess I was going to start with almost a rhetorical question. What is a regression model? Because I think if you think of all the regression models you are used to using, and then you are trying to describe to someone what links them together, what binds them together, it's quite difficult because there are so many and they're used by so many different people in different ways in different disciplines. But I think we would probably all agree that one thing that maybe binds regression models all together is that they are, at their heart, in some sense, an expression of some conditional distribution of an outcome given covariates, and that they are used in some way to answer the question, how does this conditional distribution vary for different values of the covariates? And I think one really important feature of all regression models is that they are, in some sense, to some degree, parsimonious. In other words, they encode assumptions such as no effect modification that allow you to share the same parameter for two, in principle, different valued effects. And I think this is the case even if, in fact, you fit a model that does allow for a certain amount of, you include some product terms because you think there is some effect modification, you're probably, if it's a meaningful regression model and not just a trivial one, then at some point somewhere in the model, some parameters are being shared to, so the same parameter is used for, in principle, different quantities. So there is some kind of parsimony. Otherwise, I don't think we would bother doing it. And since this is a series on causality, I thought I should have a slide on how regression models are used in causal inference. Again, only by means of introduction. Of course, you all are very familiar with this. So in the traditional approach to drawing causal inferences from observational data or even from randomized experiments, regression models are often used. And really there, in the traditional approach at least, one single regression model usually is the analysis. So you put in your exposure or treatment of interest, you put in some other covariates, either because they're confounders or for some other reason. And then the coefficient of the exposure or treatment in that model becomes the effect of interest. Yes, and that's conditional on the other variables in the model. Whereas maybe in what we call causal inference approaches, often many regression models contribute to the analysis. And then some manipulation of the coefficients or the predictions form the effect of interest. And one important feature, I suppose, is that the outcome is not always the outcome. So if you think of propensity score models, some of the models involved in instrumental variables where you're modeling the exposure given the instrument, or G formula where you're often modeling the time varying confounders given the history. So there are many examples in causal inference approaches where there are many regression models, and the outcome in any given regression model is often not the outcome in the entire analysis. And then finally, of course, regression models are often included as part of an ensemble of learners in the more machine learning and data adaptive approaches to causal inference. So regression models come in many different ways, I suppose I'm just trying to say. And so why should we care about, let's say, correct specification of these models? Or indeed, if we are trying to suggest now a regression by composition framework, which I'm going to come on to, which we are claiming is a bit more general and includes some models that are not included in our standard toolkit, then why do we need this flexibility? Why do we need yet another model that perhaps has the chance to be better specified than the ones we might be able to specify already? And of course, that's really at its heart all to do with the fact that a wrongly specified model leads to bias in general in the estimated effects of interest. But this is particularly bad if we're transporting estimated effects to a new context. And so an excellent example of this is if you fit a GLM with a log link, for example, so for a binary outcome. So your estimated treatment effect is a log risk ratio. Then if you had coded your data differently and you just swapped the meaning of the outcome between 0 and 1, so if you were, let's say, modeling death as the outcome and now you model survival as the outcome, you will get a different conclusion if you use that. So the risk ratio becomes a survival ratio. And if you use that to predict the risk for a new patient that has a different baseline risk from the ones in your study, then you can end up with very different conclusions if you're transporting based on a different effect measure. And this, I think, people just generally find uncomfortable. And again, if you use the risk difference or an odds ratio, you would get different conclusions again. And even, let's say, with a machine learning approach, for example, superlearner, then for modest sample sizes, one often finds that some parsimonious regression model that you've put into your learner can win, as it were, above the rest, or be given a lot of weight in the ensemble. So I think the quest to search for a well-specified parsimonious regression model still remains, even if you are using these more flexible techniques such as ensemble learning. So the plan for today then is that I'm going to introduce regression by composition, focusing mainly on binary outcomes for simplicity. And these are a large class of regression models that include, for example, GLMs and GAMs. And they're formulated in a way that we feel anyway emphasizes some of the key properties of models and hence of effect measures that are linked to models and of the parsimonious homogeneity assumptions that one is encoding in a regression model. And as I said, this framework permits useful new models that are not GLMs or GAMs, for example, ones that parameterize effects as switch relative risks. This is one of the main motivations, certainly one of Anders's main motivations for developing this framework, was he wanted to find a regression model that had a switch relative risk as its natural parameter. So I'm going to have a section where I briefly describe to you what the switch relative risk is and why we might be interested in using it as an effect measure. And then I'm going to talk a bit about the fitting of RBC models, which is quite a natural thing to fit using maximum likelihood. And I'll just give some of the nice features of that fitting algorithm that we've been exploring. And then finally, I might have time to say a little bit about for example, RBC models for survival outcomes and other extensions. Okay, so I'm going to try to first have an informal introduction to regression by composition before moving on to a more slightly more formal descriptive definition of what a regression by composition is. So I've taken the data from this 2017 Nature paper, which is an RCT with around 4,500 participants, newborn infants in rural India. And it's an RCT comparing oral symbiotics versus placebo, with the primary outcome being death or sepsis within 60 days. So the aim of the oral symbiotics is that they will reduce infection, hopefully, and therefore reduce the chance of resulting sepsis and death. There are very few deaths in the study, in fact, so you can think of it as sepsis within 60 days as the binary outcome. So the reported result in the paper is that there was a 9% risk of sepsis in the placebo arm versus a reduced 5.4% in the active arm. And they expressed this as a risk ratio 0.6. And this was marginal, it was unadjusted. And even though they did measure some baseline covariates, they didn't use them in the analysis. And so in the introduction to the paper, or maybe in the abstract, when they draw their conclusions about the treatment effect, they used some language that did sound a little bit as if they were justifying their use of the risk ratio as an effect parameter, using some of the arguments that Anders has been exploring with the switch relative risk. So this paper sort of called out to us a little bit as a paper that might be useful to explore the framework and the resulting fitting methods that we've been thinking about. So I'm really going to use this for illustration. I'm going to adjust for sex of the infant and the mother's age and parity, just as an example of covariate adjustment in this data set, some covariates to condition on. I mean, in fact, I think it's not the most interesting analysis because there is reason to believe that there might be effect modification by birth weight and gestational age. For example, that the symbiotics work differently for babies with a particularly low birth weight, whereas I don't think there's any particular reason to think that there's effect modification by the sex of the infant or the mother's age or parity. And so it's perhaps they're perhaps not the most interesting covariates to be adjusting for, but I'm going to use this really for illustration, just to show that first to illustrate what an RBC model is, and then maybe to demonstrate that at least we can fit these models to some actual data. So first of all, I've just put up the logistic regression table that you would get from any standard software if you just fitted a logistic regression model as we are used to doing, with no product terms here. So it's a main effects logistic regression. And we are all used to interpreting the baseline log odds and then these estimated log odds ratios for the different variables, and including the treatment effect minus 0.58. And what I want to do first is to talk to you about how you could view this as a regression by composition. So the key element to a regression by composition is to think about a sort of risk changing machine, really a distribution changing machine. So we think of a regression model as something that starts with an initial distribution and then changes that according to the covariate information until you get to a fully conditional distribution that is conditional on all of the covariate information. And for binary outcomes, the distribution is just expressed in terms of one parameter. That's why it's a simple example. So we can write the distribution in terms of just P, the probability of the outcome equals 1. And you can think of logistic regression as employing this machine, if you like, but we are going to call them flows. And what that machine does is it takes an input risk and it gives you an output risk. It transforms it to an output risk using an effect size eta. So for logistic regression, first you take your initial risk. So this, for example, could be the risk for the group in which all of the covariates are at their reference. So this could be mother's age. I haven't centered it, so it's the nonsensical mother's age of 0, mother's parity being 1, sex being female, and randomized arm being placebo. And then if you take the logit of that risk and add some real number to it, eta, and then take the inverse logit of that number, you're back to another risk. So this would, so for example, if the eta is the, let's say, the effect of having parity 2 rather than 1, you would add this, whatever it is, 0.4057, that would be your eta. You would add that to the logit of P, and then you transform back to the risk scale, and that would give you the risk for someone who is still at the reference level of everything else, but has level 2 of mother's parity, for example. And so you can imagine that so this relationship that takes P to FP, or actually we sometimes write it PF, and that's how I've written it here with function application on the right. I thought I'd switched them all back, but I've missed these here. So PF just means F of P. And depending on what eta is, that sort of, we think of the F as the machine, and then the eta is like the setting on the machine. So if the eta is very large and positive, you'll be picking out a function that looks around this end, and if it's very large and negative, it's going to be here. And if eta is 0, then you just get the identity F of P equals P, and yeah, modest effect sizes are here, and as you move further away, you get larger effect sizes. So this is just a way of thinking about what logistic regression is doing. For sort of convenience only, really, we start with an initial risk that has nothing to do with the data. So, for example, 0.5 is a sensible choice for logistic regression. That means that you can, the only reason for this is that it means that the intercept isn't a different beast. It fits in with all of the other coefficients. So if you start from 0.5, then you apply the intercept flow. So the intercept coefficient here is minus 1.814. So if you, so I didn't say, but you can rewrite this as this slightly nicer looking expression. So if you feed that value of eta into the logistic regression machine plus 0.5 for P0, you end up with P1, which is the baseline risk. So that's the risk at the reference level of all covariates. And you can think of that, you know, I've just done a graph of this. So this is just picking out the the curve here that corresponds to that particular value of eta. It's not a very sensible thing to do because, of course, this meaningless flow, if you like, is just to get things going. And really, this is only taking 0.5 to something just under 0.2. So it doesn't really matter what the rest of the curve looks like. But still, in its engine, as it were, that's what the logistic regression intercept is representing. And then, if we go on to mother's age next, so you can now put this estimated coefficient, which is not eta now. So eta, the setting on the machine is a combination of the coefficient that's been estimated, or the coefficient to be estimated, if you want to think of it that way, and the value of the covariate. So for the intercept, everyone has value 1, but obviously for mother's age, everyone will have a different x2 potentially. So eta now is minus 0.06, so 6 times x2. But that again gets just fed into the machine, and out pops now a new risk, which is the risk for someone who is, or the predicted risk for somebody who is at the reference level of everything else, but has their value of mother's age. And so on it goes. So the maternal age flow can be visualized again in this way. And now there is more of a sense to looking at the curve here, especially because the curve is different for every different value of x2. In fact, I'm wrong to say that this is more natural, because again, we've only got one input risk, which is the baseline risk. So it's just under 0.2. So everyone will actually be starting here with their input risk, and they will get an output risk, which is one of these implied by whichever of these curves is relevant to them based on their value of mother's age. But now we do have a spread of different risks that the maternal age flow has outputted to us, so that when we go on to maternal parity, if that's the next one in our sequence, then whichever input risk you have here, which is now your input risk given your maternal age and reference level of everything else, will then get transformed either it will be left alone if you have parity 1, or it will be transformed to the corresponding place on this curve if you have parity 2, and the corresponding place on this curve if you have parity 3, and so on. And so now, yes, you've got, as we're all used to the fact that we have 3 different coefficients, 3 different possible values of eta based on your x3, and so on. I won't go through it now. For the male sex, a similar thing happens there, and a similar thing for the treatment effect. But this perhaps is the one that we're really interested in. So this minus 0.58, this is how that curve looks like if you pick out that value on your initial set of pictures for logistic regression. And so the data are still down here somewhere. And so whatever your input risk is based on your values of all your covariates, but at the reference level of treatment, which is placebo, this is what you would get, which is because this is underneath the 45-degree line, you would get a slightly lower risk because this is negative for your risk given all your covariates and if you're in the active arm, so your treatment status as well. So I think this emphasizes this transportability issue, or this extrapolation. So this, if you were to use the output of a logistic regression model to predict what would happen on active treatment for someone with a placebo-based risk based on their covariates of, let's say, 0.8, then you would be taking them up here to 0.7 based on this, extrapolation of this curve up here. And of course, you can add the 95% confidence intervals. I lazily wasn't including them, but at each stage you could evaluate, the same function at these confidence limits of your coefficients to get the confidence interval for the flow. And then you can view the entire model as the sequence of these machines. So you start with an input risk here, it gives you an output risk. That becomes the input risk at the next flow. And then depending on your covariates, gets transformed to your output risk. And as I say, the data are all towards this low end here. But by the end, we have a spread of risks based on covariate information that gets transformed from the placebo to the active arm, which is what we're interested in. But really, the data are all down here. So that was a sort of tedious way of going through a logistic regression model that everybody already knows and loves. But just to emphasize how one can quite naturally think of that model that we already understand as this sequence of transformations of risks. That's all I was trying, that's the point I was trying to make. So this idea that, and more generally, that you can start with a distribution, do something to it based on your first bit of covariate information, do something else to it based on your next bit of covariate information, and so on to the end. It is already there, even in the models that we know. So more formally, a regression by composition consists of some initial outcome distribution, P0. So I'm going to try to use the blackboard P to show a distribution. So this could be the law. We're not only talking about binary outcomes, but for binary outcomes, this is just the single P, the probability of Y equals 1. And then inherent to our scheme, if you like, is an ordering of the covariates. And this is different from, most regression models. You don't have to have an order for the covariates in mind. And of course, often it won't matter for us either, but the framework, at least in principle, has an ordering of the covariates. So we have the covariates X, and I'm going to write X1 to Xm, not to mean necessarily, that X1 is just 1 for everyone, because that's the intercept. X2 is, mother's age, X3 is mother's parity. Instead, X1 is just the reference value of everything. Then X2 is the reference value for most things, but non-reference for something, for example, maternal age. And then you sort of build up your covariate information until you end up with the full set X of covariate information. And then we're also going to think about increments in that information. So delta X1 is what you learn at the first step, which is nothing. Delta X2 is like what you learn. So often it will be the difference between X2 and X1, but not always, because these things, they don't have to be even real valued, and they can certainly be vector valued, and they can be, but the notion still is of a difference between X2 and X1, and that's delta X2. So that's the new things that you learn at the new stage of the model. And crucially, that can include previous values of the previous covariates, and that's how we encode interactions into such a model. But also they can be basis splines, for example. So they can be as flexible as we are used to in other contexts. And then we have a local linear predictor, eta j, which often will just be the vector delta x, the row vector delta xj times the column vector beta j. But we allow more complicated things, like, for example, when we talk about survival analysis, eta j isn't just a number, it's a function of t if you want to allow for time varying effects. And then, for example, your wj could be a vector of now maybe basis splines for log time, for example. But often for many examples, the ones I've shown so far and that I will show in this talk, wj is just 1. Okay, and then finally, we need a flow, or sometimes a semi-flow, but I'll talk about that in a moment, a flow fj for each j, so that the composition, so you start with P0, you apply F1 to it at setting eta 1. Then you apply F2 to it at setting eta 2, and so on until you finally apply Fm to it at setting eta m, gives you P, which is up to the unknown parameters, the posited conditional distribution of the outcome given all of the covariate information. So this is why we call it regression by composition, because it is the composition of all of these flows, or if you like, effect functions that are transforming the distribution. So the logistic regression flow that I wrote up before is this one. And of course, more generally, a GLM with link function G would just be G to the minus 1, G of P plus eta. So you take it to the scale of the linear predictor, whatever that is, then the effect is to add some number to that, and then you take it back to the risk scale using G minus 1. And then you can see that if you compose several of these with the same G, then the G and the G minus 1 will keep cancelling. And so really you end up with just GP plus eta 1 plus eta 2 plus ... plus eta m, all G inversed. In other words, all the flows contract into one big flow with an effect parameter, an effect size eta 1 plus eta 2 plus ... plus eta m. So in other words, that's what we should expect, because we know that that's the central feature of GLMs, that there is a single linear predictor where you add up all of your covariates multiplied by your coefficients, and then you apply one common link function to map that to the expectation of the outcome. So what's different, therefore, for RBCs compared to GLMs is that we don't insist that all of the Gs need to be the same. So we permit different link functions for different covariates. And this is very similar to the Cox-Orlan model in survival analysis, if you're familiar with that, where you have an additive hazards component and a multiplicative hazards component in the same model. So this is really exactly an example of having different Fs for different covariates in the model. But also we permit Fs that cannot be written in this GLM form. So there might be some Fs that we're interested in that aren't just G to the minus 1 of G of P plus eta, and for any such G. So I will give you an example of that, which is the switch relative risk. And the other difference is that we can take any outcome distribution P0 as the input at the beginning. So most, well, GLMs are written within this exponential family. So the regression model tells you what to do to some input distribution, like Poisson or normal or whatever, depending on the link function you're using. But it doesn't tell you, or depending on the outcome distribution you're assuming within that exponential family, but it doesn't tell you what to do with, you know, what does it mean to apply Poisson regression to a mixture of two Poissons, for example. That's not encoded within the GLM, whereas an RBC has to be able to tell you what will happen to any input distribution. For much of, or certainly for binary outcomes, of course, that's not relevant because the input distribution is trivial and covers all bases. But it is important for other kinds of regression models, for non-binary outcomes. So just a few more words on flows. So a flow generalizes the notion of function iteration to non-integer values. So for that reason, we'll often write f of p and eta as f to the eta of p. And that is really because it is, you know, if this is an integer, then f squared of p is f of p composed with, f composed with f of p. So the two non-trivial flow properties are that f0 of p should give you p, and that f eta 1 plus eta 2 of p should give you the same as f to the eta 2 of f to the eta 1 of p. So I think these are both important. They're not actually, you could carry out the estimation of the model without these properties, but I think it's just a sensible property for a regression model to have, at least almost, because we are going to permit semi-flows in a moment where this second property holds only if eta 1 and eta 2 are of the same sign. But this is really what allows that parsimony that you need in a regression model, that you can, so if you've got a continuous covariate, you need to be able to say, at least on given some transformation, that a unit increase is the same at different levels of has the same effect at different levels of the covariate. Otherwise, you're not really encoding anything in the model at all. So usually eta will be a real number, but sometimes, as I said, in survival analysis, eta may be a function. For survival analysis to be a function of time. So for example, this is the proportional hazards flow with time varying coefficients. So S is now the survivor function, and the flow that is corresponds to a proportional hazards model is the one that transforms the survivor function to the power e to the eta of t. And when composing two flows, sometimes the order matters. So yes, for a minute I was worried that what I'm saying now is contradicting what I have up here. Of course, here it's the same f that is being composed, and then f to the eta 1 plus eta 2 has to be the same as f to the eta 2 of f to the eta 1, which is also f to the eta 1 of f to the eta 2, of course. But if you've got different flows, f1 and f2, then applying f1 and then f2 might be different from applying f2 and then f1. Often it isn't, and of course for GLMs it isn't, because just adding eta 1 then eta 2 to the linear predictor must be the same as adding eta 2 then eta 1. But for example, for the switch risk ratio flow that I will describe, this commutative property is not held. So here are just some other flows. So I showed you the picture for logistic regression. Here's the picture for a GLM with an identity link, for a GLM with a log link, GLM with a complementary log link, which is the same as kind of switching the coding of the outcome, and then applying a GLM with a log link, probit, log-log, complementary log-log, and quotient. So these are all things that you can fit, for example, in a GLM in R. And what is, so here we have, I'm just stressing, we have the input risk along the x-axis and the output risk along the y-axis. And this just shows how that gets transformed as implied by a given model with a given link function. I'll come on to the switch relative risk in a minute, but these are the other commonly used or sometimes not so commonly used GLM links. And so what are the properties? So one thing we like about this way of thinking and looking at these, and by the way, these plots are not new at all. I've called them Labe plots here because I think in 1987 paper, these were being used by Labe and others. And then in 1993, there's a very nice paper by Neuhaus and Jewell where they use these plots. So these certainly are not new, but maybe building a regression model purely on the basis of these kinds of functions is perhaps what we think is new. But it's very useful to look at these pictures to understand the model and the corresponding effect measures. So one thing that you see is that some of them are closed and some are not. By closed, I mean, can you escape through the roof, through the ceiling here, or through the floor? So given that you start with an input risk between 0 and 1, are you guaranteed to end up with an output risk between 0 and 1? And the answer is no for the GLM with an identity link. That's why people tend to be critical of linear probability models. You can also escape through the ceiling if you're using a log link. You can escape through the floor if you're using a complementary log link. But for all of the others, you see you stay inside the room. But another property you can see from these pictures is collapsibility. So essentially, if you've only got straight lines, then the effect measure that you're looking at is collapsible. And if you've got curves, then the effect measure is not collapsible. And I won't go into all the details about why that is, but it essentially follows immediately from Jensen's inequality applied to any sort of curve. So if you've got a curved relationship between the risks, then if you average the risks and then apply F, it's going to be different from if you apply F and then average the results just by Jensen's inequality. But of course, if you've got straight lines, then it doesn't matter if you do the averaging or the application of the function first. So we've got collapsible effect measures for these straight line ones, but all of these curved ones give rise to non-collapsible effect measures. And I always used to think that that was the price you had to pay to stay inside the room. You have to bend so that you either have collapsibility or closure, but you can't have both. And that's why this switched relative risk flow is such a nice one, because what it does is it takes the non-problematic half of the complementary log flow and the non-problematic half of the log flow and ends up with something which is both closed and collapsible. So I see that I'm running out of time already, so I will quickly give you a little bit of information about this switched relative risk, but I will go through this part rather quickly. So I think in a way I've already described it as best as I can using this picture. So this is an effect measure that if the covariate you're looking at, or let's call it an intervention, and let's imagine it's the sort of thing you're interested in the model. If that intervention lowers your risk of the outcome, then you take the risk ratio, whereas if it increases your risk of the outcome, you take the survival ratio. So it's a sort of disjunctive effect measure that chooses one sort of flow if eta is negative and a different kind of flow if eta is positive. So this is the risk ratio flow, this is the survival ratio flow. And in fact, it's a semi-flow rather than a full flow, this disjunctive one, because you can only claim the second flow property for values of eta of the same sign, but it doesn't actually cause any problems for the estimation that we don't have a full flow. And so this effect measure has a very long history. In a 1958 paper, Shall We Count the Living or the Dead?, Mindel-Sheps suggested that we should use the standard risk ratio when the intervention reduces risk and the survival ratio when the intervention increases risk. So exactly this thing. Then in 2007, Van der Laan and others sort of called it the switched relative risk in a more formal way, an effect measure that automatically selects the version of the relative risk recommended, but the same idea as Sheps. And then independently, many people have rediscovered the same idea in a remarkable number of different papers from different fields. And there is a rationale for why this is a good effect measure. And I prepared some slides on this, but I think perhaps I should skip these in the interest of time. Also because maybe the slides will be made available at the end if people are interested. And also because here I've included a link to a talk that Anders Whitfeldt gave that was entirely on the contents of these 3 slides that I've tried to rush them into. So in any case, you would get much more out of watching this talk. But for now, perhaps trust us, although to be honest, not everybody agrees with Anders and others on this. So I'm not saying this is completely uncontroversial, but my hope in these slides was to convince you that there is some there is some need for a model that can estimate such switched relative risks. Of course, if you don't agree with the arguments that Anders makes in his talk and the paper that goes with it, then you might disagree, in which case you might not see that there's much point in having regression by composition. But this is one of our main motivations for wanting to have regression by composition, is that it permits a model that estimates this switched relative risk, this slightly strange disjunctive parameter, but that does have some very nice properties. So quickly, the modular nature, because I think this is one of my favorite sort of features of this framework, is that the estimation itself is extremely general. You can do maximum likelihood estimation without, as a user, needing to be able to write down the likelihood of your model, if you see what I mean. So I'll try to explain. So because it's so modular in nature, the parameters are very amenable to maximum likelihood estimation. So remember that we start with a distribution and it's almost an arbitrary reference, no parameters to be estimated in it. Then it gets transformed to P1 using eta1 by the flow F1. Then it gets transformed, and the data are coming in here, by the way. It's the data combined with beta1, the coefficients, that gives you the eta1, the sort of local linear predictor, and so on until you reach your final PM. And then if you imagine an additional function that then maps that PM to a log likelihood contribution, then you've got everything you need for doing maximum likelihood estimation. For example, the score contribution is just going to be the derivative of this L with respect to each of these. Oh, sorry, this should be beta M and eta M here, not 4. And you see that there's only one path from L to each of the betas. And so there's this, so by the chain rule, and actually you need to use an exotic form of differentiation called Fréchet differentiation in general, because these are laws and not numbers. But that's a small point. But the Fréchet derivative can be used, and the version of the chain rule for Fréchet derivatives can give you the score function in terms of the derivative of L with respect to P, and then the derivative of each F with respect to both P and eta. And then you sort of trace back, the final derivative is trivial because of the local nature of the linear nature of the local linear predictor. So for many outcome types, the estimation can then proceed by Fisher scoring. In fact, for censored survival outcomes, that's not so nice because you don't want to take the expected score because that depends on the censoring distribution. So there's you then just redo the whole thing. You do another round of differentiation, sort of a cascade of chain rules across this diagram to calculate your information matrix. But I think the reason I'm emphasizing how this works is that conceptually this gives a very general fitting algorithm. So the user can bring their own collection of Fs, and as long as they also provide their first derivatives, and sometimes we need the higher order for the survival case, but for most outcome types, only the first derivatives, then this general fitting algorithm just proceeds because this part doesn't change. So they don't need to be able to write down the entire likelihood and maximize it. They only need to tell us what their particular F is and how it's differentiated with respect to P and eta, and what collection of Fs they want to use. So when we eventually come down to an R package for this, which we've started working on, we will have a huge collection of Fs that we've already programmed, but then the user can also bring their own F and have their own regression by composition that's specific to their needs. This is just to say, if you're worried that you can't differentiate the switch relative risk with respect to eta at 0 because of this strange switching, then just to say that that's actually not a problem, even though on the face of it, it may look like it's a problem, but it isn't. So the next slides were just to convince you of that, but I will, I think, skip those in the interest of time. But yeah, trust me that there isn't a major problem because of this switch at 0 here, even though you don't have a derivative there. And so this is just showing, I guess, on the example data set from nature that we can do it. So this is a model that probably you would never want to fit, where just for the sake of it, I've chosen a different GLM link function for every covariate just to show that it works. And that's the sort of picture that you get, which is now quite different because of the different nature of the flows that we've chosen. And one that we think maybe is more of practical interest would be one which fits logistic regression to the covariates, but then the switch relative risk to the outcome, to the treatment effect, to the effect you're actually interested in. So you end up estimating, because it's negative, this is a log risk ratio. But for example, this can now be compared to the effect they reported in the paper, because risk ratios are collapsible, whereas the odds ratio I showed you before, the log odds ratio, could not be compared with the log odds ratio from the paper because it was now conditional on covariate information. And in fact, if you go back to the paper and transform this back onto the risk ratio scale, you do find that there's a tiny bit of precision gained, as one might expect from having adjusted for some baseline covariates, but it's actually quite small. But it gives you, you might not have done that because you would have worried that you don't want to fit a GLM with a log link because it's not closed, but you could instead have chosen the version with a switch relative risk without having to worry about non-closure and still keeping the nice collapsible nature of the risk ratio or the survival ratio, but in this case, it's pick the risk ratio. Of course, this is the confidence interval here doesn't overlap 0. These disjunctive effect measures get more interesting to interpret their confidence intervals when the confidence interval does span 0, because obviously the interpretation is different on one side from the other. So it's quite an interesting confidence interval, I suppose, when it does do that. And we've worried about that and what does it mean? But I think it's still, if you think of the confidence interval as the kind of values of the parameter that are broadly consistent with the data, then in that sense, I think the disjunctive nature of the effect doesn't really matter. And that's the picture you would get from that model fit. And again, stressing where the data are. And then maybe finally, I just show the fitted treatment flows from the 3 models that I showed you. So the green one is the logistic regression that we would typically usually do. The blue one is that silly one where I just included all kinds of different link functions just for the sake of it. And then the red one is the switched risk ratio, for the switched relative risk for the treatment effect, and the logistic regression for everything else. And they actually look really quite different, especially up here. I mean, for example, the blue and the green lines are sure of that one gets mapped to 1 at the extreme, whereas the switch relative risk is not at all sure of that. And that's just because of the different assumptions made by the different models. It's perhaps interesting to note that where the data are, then the 3 fitted flows don't differ so wildly at all. So this really emphasizes that point that I made right at the beginning, that it's when you're transporting effect estimates from a particular study and applying them to someone with a different baseline risk or a different risk on placebo based on their covariates, and trying to infer what their risk would be on the active treatment. That's where it really matters which of these flows you're using. And so just some final remarks. So we think anyway, and I hope I've convinced you to some extent, that the RBC is a natural way of viewing a large class of existing parametric regression models as a sequence of transformations of conditional distributions. And many features of such models, such as collapsibility, follow from the properties of the constituent flows. Useful new models arise from this general framework, for example, models that are directly parameterized using the switch relative risk. And the modular nature of RBC lends it to maximum likelihood estimation and inference using, Newton-Raphson or Fisher scoring type methods. And an important extension, we think, is to survival analysis. So at the moment, we are working on a closed Olin model, that's what we're calling it, which is basically a switch relative risk model for the survivor function at each time t. So the nice thing about this model is that it allows the effect to change sign during follow-up. So you can have it very naturally, in a way that is both closed and collapsible, accommodates effects. For example, that maybe a particular surgery is initially dangerous because you might die during it, but then in the long term is protective. So you'll get an initial positive eta of t, and then it will at some point become a negative eta of t. And this is a very nice way of incorporating those kinds of effects. We believe, finally, that there are possible applications in many areas, but for example, covariate-adjusted IV regression for binary and survival outcomes where non-collapsible effect measures can cause problems, then this might be a possible solution in that area, even though I'm aware there are many other solutions that people maybe are happy with, but it's another possible candidate for those kinds of scenarios. And I didn't think I had too many slides and that I would finish very promptly, but I must have slowed down and still used almost the entire hour. So apologies very much for that, but thank you for your attention.